Trig lesson. Okay, so I've had a hard time making a trig video because trig is something so huge and something you started learning in geometry and then learned again in algebra 2 and then learned again in pre-calculus. And now to talk about it again in calculus, like what am I supposed to say that is super important? But trig is incredibly important, and not everybody has gotten the same experience throughout the years, and not everybody has a strong understanding of trig, and so I'm making this video. The reason why trig is really important for calculus is we're studying curves, and a lot of things that curve in our lives around us are like waves, or in the ocean, or electronic waves, or radio waves, or any of those kind of things. And those all follow the sine curve or the cosine curve, and they describe an incredible amount of what goes on around us. And so, since we care about things that are changing, and those are things that are changing frequently, we care quite a bit about trig in calculus. So, I'm going to start off by talking about the unit circle. Now, the unit circle is incredibly useful for ballparking what values should be. It's also incredibly useful for solving problems that need to be solved without a calculator, because they're always going to use nice trig values that you could figure out by looking at the unit circle. It just kind of builds understanding, and so being able to fill it in is incredibly useful. So I'm going to kind of run through. The unit circle starts at 0 or at 360. Usually people have an easy time with the degrees, but the radians are a little bit of a harder part. So 0 to 2 pi. And then as we go up and around, we get pi over 6 for radians and 30 degrees. If you're having a hard time filling in any of the radian ones, always just remember that 180 degrees is pi. So 30 degrees is 1/6 of 180, so it's pi over 6. But the degrees are usually what people have an easier time filling in, so maybe I'll just go through and do those first. We're going up by 30s for these guys, and then doing the one in between, the 45-degree angle ones, as we go across. So when I give people unit circles, this is usually the first spot they go, because this is the easiest thing to do in a unit circle, is to go through and do all the degrees. Alright, now that I have all these, then I can go through and do the radians. If you've done all the degrees, just do your degree measure divided by 180, and then multiply that by pi. So 45 goes into 184 times, so it's pi over 4. 60 goes into 183 times, so pi over 3. 90 goes into 180 twice, so pi over 2. 120 goes into 180 3 halves times, so it's 2/3 pi. 135 is 3/4 pi. And 150 is 5/6 pi. If you're like, man, I can't, that math is a little harder, doing 120 divided by 180, like simplifying that to 2/3, there's kind of another easy way to think about this. When you're looking at pi over 6 here, well, this guy's just going to be pi, which is 180 degrees, minus pi over 6, which is 5 pi over 6. Pi minus pi over 4, which is 3 pi over 4. Pi minus pi over 3, 2 pi over 3. So that's another easy way to fill in the radians. And then we're going to apply that same logic. Pi plus pi over 6, 7 pi over 6. Pi plus pi over 4, 5 pi over 4. Pi plus pi over 3, 4 pi over 3. And then we get to 3 pi over 2. Pi plus pi over 2. And then we just do the same thing again. So pi plus 2/3 pi is 5/3 pi. Pi plus 3/4 pi is 7/4 pi, 7 pi over 4. And then lastly, we're just pi over 6 less than 2 pi, so we're 11 pi over 6. So that's how you figure out all the radians as you go around the circle. Now, a lot of people ask, like, why do we even care about the radians? Well, in calculus, we almost solely care about the radians. Degrees are stupid. Degrees add up to 360 because there are about 360 days in the year. If you go to a person who's standing on the edge, so if you have a big field with a big circle drawn on it, and somebody's at the edge, and you want them to move a certain amount around the circle, and so like they can see the circle like in the grass or whatever, and you ask them to walk along the circle 50 degrees, how the heck are they going to do it? Oh, they bring their compass. No, that's not how they're going to do it. Now, if you tell them they need to walk 1 radian across the circle, then they might turn around and say, okay, well, how big's the radius of this circle? And you'd be like, oh, it's 40 feet. It's like, cool, I'll walk 40 feet around the edge of the circle, because radians are radiuses along the edge of the circle. So radians are just incredibly more useful than degrees, and so we use them basically all the time from this point on. Okay, my radian diatribe aside, now we got to start filling in the values. It's just over and up. So 1 and 0 is our starting spot. We got our -1 and 0. These are the easy money ones. 0 and 1, and 0 and -1. Okay, now we have the harder ones. The way to remember how to fill these in is to look at a 30, 60, 90 right triangle. So this is the 30, the 60, and the 90. This is one of the special right triangles from like the SAT and all that garbage. And the way to remember this is, x. The 30-degree side, so if the hypotenuse is x, the 30-degree side is always half of that. And the 60-degree side is always √3/2 times x. So, if we have this information, we can figure out that this is a 30, 60, 90 right here. The short side is how far up we are, so that's the sine. That's going to be half. Oh, yeah, this is a unit circle, so this distance is 1, which is why that is a half. It's half of 1. And this is √3/2. All the pi/4 ones are super easy because they're all √2/2 for both, and you just got to figure out which one's positive and which one's negative. In this spot, you're going over in the positive direction and up in the positive direction, so they're both positive. Oh, look, that is writing, and I didn't want it to. All right. And then this one is going to be 1/2 and √3/2 up, because this time my short side is the over side, and my going up side, this one, is the √3/2 side. Okay, now we just continue to the other side. Same idea. Our short side is how far over we are, but it's negative this time because it's going in the negative direction. And we're still going up, so it's still √3/2. It's negative √2/2, and √2/2 up. It's negative, well, let's see, we're going over √3/2. That the side to side is longer, and 1/2 up. And then so on and so forth. We're negative √3/2 over. We're negative 1/2 down. Here, it's negative and negative for both of them. So negative √2/2, and negative √2/2, and negative 1/2, negative √3/2. At some point, this becomes much easier. 1/2, negative √3/2, negative √2/2, whoops, positive √2/2, negative √2/2. And lastly, we have √3/2 over, and down negative 1/2. All right, and that's the unit circle. We're going to use this to solve problems in just a little bit, but yeah, that's how you fill that thing in. All right, So converting to and from radians, we kind of talked about that as we went through here, but it's really, really easy. If you have radians, you just multiply that by 180 over pi, because that's how many degrees are in pi radians. And if you have degrees, you just multiply by pi over 180. So it's pretty effortlessly easy. If you have like 5 radians and you're like, oh, I have no idea how many degrees that is, you just multiply by 180 over pi, and you realize that it's, 900 over pi degrees? Wow. So ballpark like 280 degrees or something. And same thing for degrees. Alright, lastly, I'm just going to knock out a few problems. This is going to be quite easy because we have this table here, this beautiful unit circle. So the secant of 11 pi over 6. Alright, so we got to go back to remember what secant is. Well, secant is 1 over cosine. So all I have to do is 1 over the cosine of 11 pi over 6. I go to 11 pi over 6, I look at the x value, it's root 3 over 2. And so this is 2 over root 3. Now, in some places they say you shouldn't have a square root in the bottom. You should rationalize your denominators. In that case, we just multiply by root 3 over root 3. And we get 2 root 3 over 3. Alright, tangent of 10 pi over 6. Well, 10 pi over 6 is 5 pi over 3. So I'm looking at this spot. Tangent is sine over cosine, so that's going to be my y value divided by my x value. So it's negative root 3 over 2, which is my y value, divided by 1 over 2, which is my x value. The over 2's cancel out, and I just get negative root 3. Alright, next. This is just saying find cosecant of 3 pi over 2, because that's what pi plus pi over 2 is. So I go to 3 pi over 2, I look at my cosine, it's 0. Or, whoops, cosecant. So cosecant is 1 over sine. So I'm doing 1 over my sine at this spot down here, and 1 over negative 1 is negative 1. Sine of pi over 3 plus 4. Well, I'm just going to take whatever the sine of pi over 3 is, which is root 3 over 2. And add it to 4. So that's root 3 over 2 plus 4. There's really not a lot more to say about that one. Alright, the inverse sine of root 2 over 2. This kind of brings us to an interesting spot. The inverse sines. Some people kind of forget which domains the inverse sines work for. There's a really easy way to remember. For both sine and cosine, inverse, you're going to use the first quadrant. And then the other quadrant you use is the one that's going to have negative values of the adjacent quadrant that has negative values that correspond to your positive in that one. So for cosine, we use this one as well as the first one, so quadrant 2 and quadrant 1. And for sine, we use quadrant 4 down here and quadrant 1. So because we're using sine, we're going to use one of these. For root 2 over 2, that's pretty easy. It's right here. And so we're talking about 45 degrees or pi over 4. Alright, the inverse tangent of 1. So this is the spot where sine and cosine are the same. Wow, that's the exact same spot. And now we get to some heavier ones. 1 over the cosine of pi over 2. Well, if we look over here, secant is 1 over cosine, 1 over 0. Well, that's undefined. Easy money. Cosine of pi over 6. We look at the x value of pi over 6. It's root 3 over 2. So I'm going to write that above here. And cosecant of pi over 6, that's 1 over the sine of pi over 6. So 1 over 1/2, that's 2. So this is just root 3. And our last problem on here, tangent of pi over 4. Well, we've actually done that one quite a few times. It's 1. It's right here. Root 2 over 2 divided by root 2 over 2. And then to that, we're adding the cosecant of pi over 3. So that's 1 over the sine of pi over 3. Pi over 3 sine is root 3 over 2. So it's 2 over root 3. We are going to have to rationalize the root here. So I'm going to have to multiply everything. This is a tricky one. So, okay. So what I'm going to do is turn this into root 3 over 3. Root 3 over root 3. Plus 2 over root 3. And then I'm going to multiply by root 3 over root 3. And it turns out I wasted a whole bunch of time because I get 1 for the first term, and I get 2 root 3 over 3 for my second one. And that is our simplified answer for that. So the key for sine and cosine problems is just really having a strong understanding for the unit circle, because I was able to use the unit circle to deduce the inverse sine and tangent and all that stuff, because I just needed to know the domains for them. And to solve any of the problems, I just need to know the unit circle. Like to know the conversions, all I need to know is that pi and 180 are the same, or that 2 pi and 360 are the same. So that's why I put a pretty big emphasis on the unit circle. That's why I quiz on it during the year, because having a strong understanding of that unlocks your potential to solve trig problems like the ones down here in the corner earlier on.